Welcome viewers. In this video we will see the magnetic field intensity due to the finite conductor. The expression for magnetic field intensity due to the finite conductor. So our aim is to find the magnetic field intensity to a finite conductor, current carrying conductor at point P. The point P is at a distance d meter from the origin. Right? Now we will refer the diagram so that it will be easier. So this AB is nothing but a finite conductor in which the current is flowing. When the current is flowing through the conductor AB, what will happen? The magnetic field is produced in the form of concentric circles. Right? AB is the state conductor in which the steady current is flowing. Due to that, the magnetic field is produced in the form of concentric circles. Our aim is to find the magnetic field intensity at this point P, which is at a distance d meter from the origin, or it may be center. Magnetic field intensity at point P, which is at a distance d meter from the origin. This fine conductor is assumed to be having so many current elements. Current element means ideal. Now we consider one current element IDX at this point. There are n number of current elements available, in which we are considering one current element IDX at a distance x meter from the origin. So this angle will be theta. There are n number of current element, in that we consider one current element IDX at a distance x meter. Further we can go for integration. So the angle between this point P and A is alpha, and point P and point B is beta. So A, B is equivalent to in the angle of alpha and beta. The length AB, the equivalent angle will be alpha and beta. So for during the calculation we need this triangle. So this triangle is drawn separately. This distance is D, X and R. This will be angle theta. Now we'll see the description. A state current carrying conductor AB assumed to be formed by several segments. Such a segment is called current element. Right? There are n number of segments available. That segment is nothing but current element. In that we consider one current element IDX at a distance x meter from the origin. We consider one current element. The distance between this current element and point P is R meter. So the dH is the magnetic field intensity at point P due to the current element IDX. The H is the magnetic field intensity. dH means magnetic field intensity due to only one small current element IDX. So by integration we will get the total magnetic field intensity. Right? So the dH is the magnetic field intensity due to current element IDX. Now we start with Biot-Savart's law. In order to find the magnetic field intensity expression, we start from Biot-Savart's law. dH vector equal to ideal vector cross R vector divided by 4 pi R cube. That is the expression given by Biot-Savart's law in the vector form. Ideal vector cross R vector divided by 4 pi R cube. Here we are using IDX. At a distance x meter we consider one current element. So that IDX into R vector divided by 4 pi R cube. What is A vector cross B vector? A vector cross B vector equal to AB sin theta. So that ideal vector cross R vector equal to IDX. IDX into R vector equal to IDX into R into sin theta. Right? So A vector cross B vector is written as AB sin theta. So here one R is there, here R's cube is there, so it become one R got cancelled. So that dH equal to, now this vector, this A vector cross B vector is written in AB sin theta in a scalar form. So now it becomes scalar. IDX sin theta divided by 4 pi R square. So after simplification, what we got? IDX sin theta divided by 4 pi R square. Now we have one triangle. From that we are going to find the expression for dx and r. From the triangle we are going to find the expression for dx and r, right? So this is equation number 1. So this triangle is available. This triangle I drawn again. D, this distance is d, x and r. We'll find the value of sin tan theta. Tan theta equal to, our aim is to find the value of x and r. So that first we'll find tan theta. Tan theta equal to opposite side by adjacent side. Opposite side is d, adjacent side is x. So d by x. Tan theta equal to d divided by x, right? So interchange these two values. X equal to d by tan theta, because what we need is x. So bring this x in the left hand side, tan theta in the denominator. So x equal to d by tan theta. 1 divided by tan theta is cot theta, right? So x equal to d cot theta. But what we need is dx. So we need to differentiate on both the side. So dx equal to differentiation of d cot theta. So dx equal to minus d. So the differentiation of cot theta is cosecant square theta into d theta. So that we got minus, right? Differentiation of cot theta is minus cosecant square theta d theta. So dx equal to minus d cosecant square theta d theta. Now find the expression for sin theta. Sin theta equal to opposite side by hypotenuse, d divided by r. Again cross multiply these two, right? So r equal to d by sin theta. So r equal to d into cosecant theta. Now we got the expression for dx and r. We are going to substitute this dx and r in equation number 1. What is equation number 1? I dx sin theta divided by 4 pi r square. In this we are going to substitute this dx. Dx equal to minus, so I into dx is minus d cosecant square theta into d theta into sin theta is there, divided by 4 pi r square. What is r? D cosecant theta. So d square cosecant square theta. Dx and r values are substituted, right? Here 1d is available, here d square is available, so 1d got cancelled. Cosecant square theta available in numerator as well as denominator, that got cancelled. Now we'll see what is the simplified expression. So after simplification, what we have? Minus I by 4 pi d sin theta d theta. Minus I by 4 pi d sin theta into d theta. So this magnetic field intensity due to only one current element, small current element. By integrating on both the side, we will get the total magnetic field intensity. So the magnetic field intensity due to entire conductor can be obtained by integration. Then what is the limit for this integration? Current element has to move from B to A, right? From point B to point A. So the corresponding point B, we have the angle beta. For the corresponding the point A, we have angle alpha. So that beta to alpha, because integral is with respect to theta. If it is length, we can use this, but with respect to theta, so we are using the angles beta to alpha, right? So the limits are from beta to alpha. Now we'll substitute, now we integrate on both the side. So integral dh equal to integral beta to alpha minus I divided by 4 pi d into sin theta d theta. Minus I divided by 4 pi d is constant, it taken outside. Only we have sin theta. Integral sin theta is minus cos theta. You substitute the limit beta to alpha. So that minus I divided by 4 pi d into minus cos alpha. While substituting lower limit, one minus will be there. Already one minus is there. So it becomes plus cos beta. Minus cos alpha plus cos beta. Right? Here one negative symbol available. So you multiply inside. So what will happen? I divided by 4 pi d. This minus become plus cos alpha. This plus become minus cos alpha minus cos beta. So the magnetic field intensity due to finite conductor, the final expression is H equal to I divided by 4 pi d cos alpha minus cos beta. In this one, special condition is available. Suppose if the length is infinite, what we are assuming is finite conductor. We are assuming as finite conductor AB, the length is finite. Suppose if it is infinite, what will happen? The alpha is tends to 0 while going when the length is increases, the angle alpha is approaching to 0 and beta is approaching to 180 degree, right? So here cos alpha equal to cos 0, alpha is 0, so cos 0 means 1. Then cos beta is there, cos beta is equal to cos 180 degree, beta is 180 degree, cos 180 is minus 1. So cos alpha is 1, cos beta is minus 1. We can substitute here. H equal to I divided by 4 pi d cos alpha 1 minus 1. Already one minus is there. So it become plus 1 plus 1, 2. So it become 2. Already here 4 is there. While cancelling it become 2. I divided by 2 pi d. Right? If the length is infinite, the magnetic field intensity after substituting this value, alpha approaching to 0, beta approaching to 180, what we got? I divided by 2 pi d. So in this video we discuss the magnetic field intensity due to finite conductor. We got the expression for that, and we have one special condition when if the length is infinite. What is the expression for magnetic field intensity? Thank you. Welcome viewers. In this video we'll see the magnetic field intensity due to circular current loop, followed by the two problems. Now we'll refer the diagram. One lengthy wire is available. That wire is two ends are joined together and the circular loop is formed. One lengthy wire will be available. That lengthy wire, two ends are connected together and form the circular loop. So the radius of the circular loop is a meters. Our aim is to find the magnetic field intensity at this point P, which is at a distance h meter from the center of the current loop. This current loop is assumed to be having several current elements, n number of current elements available. We consider one current element at this point, ideal vector. The distance between this current element and point P is r meter. The h is the magnetic field intensity, dh is magnetic field intensity due to ideal. There are n number of ideal available. We consider only one ideal, so that there is magnetic field intensity also small, dh. By integrating this dh, we will get total magnetic field intensity. Right? One lengthy wire available, the two ends of the wire is connected so that form the circular current loop. The radius a. Our aim is to find the magnetic field intensity at point P, which is at a height of h meter. There are n number of current elements available. In that we consider one current element at this point. The distance between this point and point P is r meter. The angle between this r and ideal vector is 90 degree. From the diagram it is clear. So this dh is the magnetic field intensity due to this small element, ideal. So this triangle is drawn separately. This angle alpha, height a and r. So from there we can find the sin alpha. Sin alpha is opposite side by hypotenuse, a divided by r. It can be used in the derivation. Right? Sin alpha equal to opposite side by hypotenuse, a divided by r. We'll see the description. So it is required to determine magnetic field intensity at point P, which is at a height of h meter from the center of the current loop. Right? The point P is located at a height of h meter from the center of the current loop. At that we are going to find the magnetic field intensity. How the circular current loop is formed? The circular current loop is formed by wire bent in the form of a circle. The wire is bent, two ends are connected together and the circle is formed. The loop is assumed to be formed by several current elements. There are n number of current elements available in the entire loop. In that we consider a current element ideal. The distance between this current element point P is R meter. Then this DH vector is the perpendicular to the plane containing vector ideal and R. In the diagram it is clearly shown. The angle between ideal and R is 90 degree. Now we'll go to the derivation. The normal component of magnetic field intensity is given by, because due to this wire we have only normal component. There is no horizontal, there is no vertical component, only normal component. So dH equal to dH cos 90 minus alpha. Normal component is, it is multiplied by cos of theta. Cos 90 minus alpha can be written as sin alpha. What is dH? From Biot-Savart's law, the standard form is available. Ideal vector cross R vector divided by 4 pi R cube into sin theta, sin alpha. So this is written from the Biot-Savart's law. What is A vector cross B vector? AB sin theta. So ideal R into sin theta. The angle between DL and R is 90 degree. So it is 90 degree. So ideal cross R vector is ideal R sin 90 into sin alpha divided by 4 pi R cube. Now here R is there, here R cube is available. So here this sin alpha is replaced by A by R. From the triangle we calculated sin alpha equal to A by R. So this R got cancelled. Sin 90 is 1. So finally what we have? I into A into dl, IA dl divided by 4 pi R cube. IA dl divided by 4 pi R cube. So this is due to only small current element. This dH is the magnetic field intensity due to small current element. So by integrating on both the sides, we'll get the total magnetic field intensity. So integral dH equal to integral IA dl divided by 4 pi R cube. IA divided by 4 pi R cube is constant. Only we have integral dl. What is integral dl? Integral dl is L. L is nothing but 2 pi A. That is, one lengthy wire is available, length L. This wire is formed as a circle, as a current loop. So this radius is A. So the length of this wire is equal to circumference of this current loop. Both are equal. What is the circumference? 2 pi A. That is given. Length of this wire, because this wire only formed a circle. So the length is nothing but circumference. Both are equal. L equal to circumference. Circumference is 2 pi A. Right? So integral dl is L. L is nothing but 2 pi A. Here 4 pi is there. Here 2 pi is there. Got cancelled. 2 is there. So I into A square. I into A square divided by 2 R cube. IA square divided by 2 R cube. We got the value. We take it as equation number 1. H equal to IA square divided by 2 R cube. Now we'll see the other forms. So from the triangle we can write R equal to, using Pythagoras theorem, A square, square root of A square plus H square. So from this triangle it is given R square equal to A square plus H square. So R equal to square root of A square plus H square. That is written. So R equal to, it can be written as A square plus H square whole power 1 by 2. Square root is written as 1 by 2. But in equation what we have? R cube. R cube is needed. IA square divided by 2 R cube. R cube means you multiply with 3. Already 1 by 2 is there. So 3 into 1 by 2 is 3 by 2. R cube equal to A square plus H square whole power 3 by 2. Right? So r equal to square root of a square plus h square, that can be written as a square plus h square whole power 1 by 2. Here 3 is needed, r cube is needed. So a square plus h square, 3 into 1 by 2, that is 3 by 2. Now we can substitute this value in the equation number 1. What is equation 1? H equal to ia square divided by 2r cube, right? So this r cube can be substituted from this. A square plus h square whole power 3 by 2. So what will happen? H equal to ia square divided by 2 into a square plus h square whole power 3 by 2. So this is another form in terms of height. In the equation 1, what we have? A and R. A and R is available. A is the radius of the current loop, R is the distance. Here, and in terms of height is available. A and height. So this is another form. Suppose if the center of the current loop, if you consider the point P is located at the center, or what is the magnetic field intensity at the center of the current loop. So at the center of the current loop, what will happen? The height is 0. So the height is 0, so that h equal to ia square divided by 2 a square plus h square whole power 3 by 2. This height is become 0. This height become 0. So what will happen? Ia square, this a square into 3 by 2. So this 2 got cancelled. We will get a cube, right? So this what is available here is a square whole power 3 by 2. So this 2 got cancelled. What we have? A cube. So ia square divided by 2a cube. Here a square cancel, here 2 terms are cancelled. So what we have? I divided by 2a. This is at the center. At the center of the current loop, the magnetic field intensity is I divided by 2a. Suppose if n number of turns are available, what happen? ia square divided by r2 r cube into n. You have to multiply with number of turns, right? H equal to ia square divided by 2 r cube into n. That is due to n number of coils. Here we have only one circular current loop. If n number of current loop available, ia square divided by 2 r cube into n. So we have the 4 different expression available. First is ia square divided by 2 r cube. Then r is substituted in terms of height. That is the second expression. Then height is 0 at the center. That is third expression, this one. This will be fourth expression in terms of number of turns. Now we'll see the problem. We'll see the first problem. What is given? A wire carrying a current of 100 ampere is bent in the form of circle. So this is a circular current loop of diameter 10 centimeter. Right? See here, the current is 100 ampere, diameter equal to 10 centimeter means radius equal to 5 centimeter. That is 5 into 10 to the power minus 2 meter. So what is the question? Flux density at the center of the coil. First one, at the center. Flux density at a point form a axis of the coil and 12 centimeter away from it. That is at a height of 12 centimeter. Right? We discussed 4 different expressions available at the center, in terms of height, all are available. So first one is based on the center of the current loop. Height is 0. Second one based on the height. Height is 12 centimeter. Right? So the current and radius is given. Now we'll go to the first division. Magnetic field intensity at the center of the coil. What is the formula? I divided by 2a. At the center of the coil, height is 0. So only we have I divided by 2a. Already we got the expression. So I is 100 divided by 2 into a. A is nothing but radius. 5 into 10 to the power minus 2. So by simplifying, what we got? 1000 ampere turns per meter. This is the magnetic field intensity. But what we need is flux density. B is needed. So B equal to mu naught mu r into h. There is a relation between mu and h is available. B equal to mu naught mu r h. Mu naught is nothing but constant. 4 pi into 10 to the power minus 7. Mu r is 1. We assume that is a air medium. The height is, the magnetic field intensity is calculated. This 1000. Right? So by simplifying this, what we got? 1.25 into 10 to the power minus 3 Weber per meter square. magnetic flux density is 1.25 into 10 to the power minus 3 Weber per meter square at the center of the coil. We have one more at the 12 centimeter. When it is the axis is placed at a height of 12 centimeter, that is height equal to 12 centimeter. That is 12 into 10 to the power minus 2 meter. For this, what is the formula? Ia square divided by 2 into a square plus h square whole power 3 by 2. So this expression also we got previously. This is in terms of height, right? So I is 100, a is 5. 5 into 10 to the power minus 2 square divided by 2 into 5 into 10 to the power minus 2 square plus height is nothing but 12 centimeter. 12 into 10 to the power minus 2 square whole power 3 by 2. You have to square this value, add both. For that we need to take 3 by 2, right? So by simplifying this value, what we got? 57.36 ampere turns per meter, okay, at the height of 12 centimeter. This is a magnetic field intensity, 57.36 ampere turns per meter. From that we can find magnetic flux density, B equal to mu naught mu r into H. So mu naught is 4 pi into 10 to the power minus 7, mu r is 1, and the magnetic field intensity what we calculated 57.36. So by simplifying this value, what we got? 71.46 into 10 to the power minus 6 Weber per meter square. So this is due to the coil placed at 12 centimeter height, right? So this one due to it is placed at the center of the coil, right? We have two divisions, center of the coil and placed at a 12 centimeter height of 12 centimeter. Now we'll see the next problem. So in the second problem, there are two narrow circular coils available, A and B, right? We'll see the diagram so that it is easier for you. So there are two circular current loops are available. The radius of the first circular current loop is 5 centimeter. Second current loop is 8 centimeter. The center to center distance is 15 centimeter. The current flowing through the first coil is 2 ampere. Coil A is 2 ampere. But the current in the second coil is not given. We need to find, right? So the radius of first one is 5 centimeter. Current is 2 ampere. Radius of the second coil is 8 centimeter. Current is not known. Center to center distance is 15 centimeter. So what is the other values are given? So the two circular coil A and B and placed at a distance 15 centimeter. Coil A has 10 turns available of radius 5 centimeter and the current is 2 ampere. But coil B has single turn of radius 8 centimeter. What is the condition? If the magnetic field at the center of coil A is to be 0, what current must be passed through coil B, right? So at the center of the coil A to be 0, in order we need to make it as this coil A is 0 such that what is the current is passing through coil B. So that is the question asked, right? So we will see what are the data. The number of turns available for the coil A is 10, radius 5 centimeter, 5 into 10 to the power minus 2 meter, current is 2 ampere. For coil B, number of turns 1, radius is 8 into 10 to the power minus 2, the IB we need to find. So from the given condition, we can conclude that the magnetic field at the center of coil is 0. When it is 0, it is possible only when the magnetic field intensity due to the coil B, HB, due to the coil B at the center of the coil oppose the HA, which is equal and opposite, right? So magnetic field intensity of coil A, when it becomes 0, the magnetic field intensity due to the coil B oppose the coil A, and it should be equal and opposite. So the magnetic field intensity produced by coil B is opposing coil A and make it as 0. What is the meaning? Both are equal and opposite. HA equal to HB. That is the from the given condition, we got the expression HA equal to HB. So the magnetic field intensity produced by coil B oppose the coil A and make it as 0. Right? So using this condition, we can find the current in the second coil. So first we will find the HA. HA equal to NAIA divided by 2A. That is at the center. The coil A we assumed at the center. Coil B we assumed at a height of 15 centimeter. Right? Coil A is a reference. So that it is at the center. NAIA divided by 2A. Normally I by 2A, but here number of turns available, so that NAIA divided by 2A. The number of turns is 10, current is 2 ampere, divided by 2 into the radius is 5 into 10 to the power minus 2. That is 200 ampere turns per meter. So the coil A we assume at the center. Coil B, it is at a height of 15 centimeter, because coil A and B, the distance center to center distance between coil A and B is 15 centimeters. So that we are using this formula at a height, in terms of height, here at the center. So now we substitute the value. NB, the number of turns in the coil B is 1, right? Then IB value is not available. We need to find the IB value. Then B square, 8 into 10 to the power minus 2 the whole square, divided by 2 into 8 into 10 to the power minus 2, the radius of the second coil, plus the height. Height is 12 into 10 to the power minus 2 whole square, whole to the power 3 by 2. Right? So by simplifying this, what we got? 0.651 IB. Right? So HB equal to 0.651 IB. Right? This IB value is not known. Now we have the relation HA equal to HB. What is HA? We calculated 200. What is HB? 0.651 IB. So from that, IB equal to 2 divided by 0.651, that is 307.6 ampere. So the current flowing through the second coil B is 307.6 ampere. So due to this current flow, the magnetic field produced in the coil B will oppose coil A and make it as 0. So in this video, we discuss about the magnetic field intensity due to circular current loop, followed by 2 different problems. Thank you. Welcome viewers. In this video, we'll see the magnetic field intensity due to the solenoid. What is solenoid? Solenoid is an electromagnet. It is formed by winding few turns over an iron rod. So this is the iron rod is there. Over that, the coils are winded. If the supply is given, it becomes the electromagnet. So the solenoid is nothing but iron rod is available. Over that, the coils are winded. When the supply is given, it becomes electromagnet. So our aim is to find the magnetic field intensity at the center of the solenoid. It is required to determine magnetic field intensity at the center of this solenoid. Now we'll go to the detailed diagram. So the length of the solenoid is AB. We consider length of the solenoid is AB. This is at the center. Point P is located at the center. For calculation purpose, we consider one small segment at a distance x meter. The thickness is dx. The number of turns available is n into dx. So at point P, at a distance x meter, we consider one small segment dx. The number of turns is n into dx. By integrating, we will get the total magnetic field. The distance between this point P and this end is r meter. This distance is a meter. This angle is theta. So this triangle is drawn separately here. Theta, x, r and a. The angle between point P and point B is alpha. Similarly, point P and point A is pi minus alpha. So this will be alpha. So automatically the remaining will be pi minus alpha. Right. So We have the solenoid with length AB. Our aim is to find the magnetic field intensity at the center of the solenoid. So point P is located at the center. The small segment is available at a distance x. The thickness is dx. Number of turns is n into dx. This angle is theta. This distance is r. This distance is a. This triangle is drawn separately. The angle corresponding to point A is pi minus alpha. The angle corresponding to point B is alpha. Right, now we'll see the description. A solenoid is assumed to be formed by several circular current loop. Right, so the circular current loop derivation available in separate video. You can refer that. In this solenoid, what we are assuming, there are n number of current loops are available. Each and every coil is a current loop. Consider a segment of the solenoid at a distance x meter from the point P. We consider one segment dx at a distance x meter. The number of turns in this section is n into dx. Right. What is the magnetic field intensity due to this small segment? The dH is the magnetic field intensity due to n into dx turns at point P, which is given by dH equal to Ia square divided by 2r cube into n into dx. Right. So this is due to only small segment with n number of turns, n into dx. How we got this expression? That is from circular current loop. Circular current loop derivation already available in another video. Right. From that we are referring this. So this is also circular current loop. Here n number of circular current loops are available. So that is multiplied by number of turns, n into dx. This is circular current loop expression, Ia square divided by 2r cube. In that, n number of turns are multiplied. We take this equation number 1. Now we'll find the expression for r and dx from the triangle. One separate triangle is available. From that, we will find the expression for dx and r. So refer this triangle, which is already available. So I drawn again here. The angle is theta, x, r and a. Now we'll find the expression for tan theta. What is tan theta? Is tan theta equal to opposite side by adjacent side, a divided by x. Now cross multiply this. So x equal to a by tan theta. 1 divided by tan theta is cot theta. What we need is differentiation. We need a differentiation. We need a dx. So differentiate on both the side. Dx equal to differentiation of a cot theta. So the a is constant. The differentiation of cot theta is minus cosecant square theta into d theta. So finally what we have? Minus a cosecant square theta d theta. The expression for dx is minus a cosecant square theta into d theta. Now we got the expression for dx. Similarly, find sin theta, expression for sin theta. Sin theta equal to opposite side by hypotenuse, a divided by r. Again here cross multiply this. Bring the r here, sin theta here. So r equal to a by sin theta. So 1 divided by sin theta is cosecant theta. So r equal to a cosecant theta. Now we got the expression for dx and r that can be substituted in equation number 1. Right? Substitute the value of dx and r in equation 1. What is equation 1? Ia square divided by 2r cube into n into dx. This is the equation 1. So Ia square into n, dx is nothing but minus a cosecant square theta into d theta. So that is available here. Dx equal to minus a cosecant square theta into d theta divided by 2 into r cube. What is r value? R is nothing but a cosecant theta. Right? So that a cube into cosecant cube theta. The dx value substituted and r value substituted. See that here cosecant square is available, here cosecant cube is available. So these two got cancelled. Cosecant square dot cancel. 1 cosecant theta will be available. Here a cube is available, here a square and a is available. So totally all are cancelled. So finally what we have? I into n into d theta divided by 2 into cosecant theta. One cosecant theta is available here, right? So minus also there, this minus also there, minus in d theta divided by 2 cosecant theta. So 1 divided by cosecant theta is written as sin theta d theta, right? So dh equal to minus I into n divided by 2 sin theta d theta. So this is due to only small segment. So by integrating, we will get the total magnetic field intensity. Intensity due to entire solenoid can be obtained by integration. Now we'll see the integration. What is the limit for the integration? So when the length of the solenoid is AB, at the end AB the angle is pi minus alpha. So this is one limit. At the end B the angle is alpha. This is another limit. How it is? By moving the strip from A to B, the magnetic field intensity due to the entire solenoid can be obtained. Therefore the limit is from pi minus alpha to alpha. That is A to B. A is pi minus alpha, B is alpha. So the limit is from pi minus alpha to alpha, right? Now we'll go for the integration. So integral dh equal to integral pi minus alpha to alpha minus I into n divided by 2 sin theta into d theta. Just now we got the expression. So in that minus I by n divided by 2 is constant. Only we have sin theta d theta with a limit pi minus alpha to alpha. So minus in divided by 2, integral sin theta is minus cos theta with a limit pi minus alpha to alpha. Now we'll substitute the limit. Minus in divided by 2, this substitute the upper limit minus cos alpha. While substituting the lower limit, we already one negative is there, it become positive. So this will be theta, not a alpha, theta. Pi cos pi minus alpha. So upper limit is substituted and lower limit also substituted. Due to negative, it become positive. So already one negative available outside, so multiply inside, so it become positive, it become negative. In divided by 2 cos alpha minus cos pi minus alpha. So in divided by 2 cos alpha, cos pi minus alpha is nothing but minus cos alpha. Cos pi minus alpha can be written as minus cos alpha. Already here one minus is there, here also minus is there, so it become plus. So in divided by 2 cos alpha plus cos alpha. So that is nothing but in divided by 2 cos alpha. So 2 got cancelled. I into n into cos alpha, right? So the magnetic field intensity due to the center of the solenoid is I into n cos alpha. Now we'll see the one more special case if it is long solenoid. Suppose the solenoid is infinite long. If it is infinite long, what will happen? The alpha value is 0. So that cos alpha, cos 0 means 1. So the magnetic field intensity become I into n. I into n into cos alpha. The cos alpha now become 1. Right? So this is the magnetic field intensity due to infinite long solenoid. One special case. From this equation what we understand, magnetic field intensity due to a long solenoid is uniform. It does not vary with the distance. Right? So the magnetic field is uniform. Here the distance is not available. Only current and number of turns. So it means that the magnetic field is always uniform. It does not vary with the distance. So in this video, we discussed the magnetic field intensity due to the center of the solenoid, derivation, and one special case, infinite long solenoid. What is the expression for infinite long solenoid? Thank you.